Right, what we have here is a set of television deflection coils. These are very old ones, which would have fitted a tube like this one, and they were designed to provide the horizontal and vertical deflection processes for a display tube. They comprise two sets of coils with their axes at right angles, so one has an axis like that, the other has an axis like that. Now, in a television system, these would have been fed from sawtooth waveforms, one at a very high frequency for the line deflection and one at a much lower frequency for the vertical deflection. Now, in this situation, we're going to feed them from a high power audio amplifier, and that's getting its signal input from two oscillators, very stable oscillators. In this case, we're running them both at 50 Hz, and they're stable enough for us to be able to set the phase precisely to, in this case, about 90 degrees. We can investigate what's happening in the coils using this probe, which is just two small coils whose axes are at right angles to each other. If I stick that into the deflection coils, we can get an output. Okay, now just one of these coils is being energized at the moment, and you'll see that as I rotate the probe coils, we get two outputs which go from a maximum through to zero, and you'll see that one is maximum, the other is zero, and vice versa. And also the phase inverts. If I rotate by 180 degrees, the phase inverts completely. Okay, now another way of looking at this is to put the oscilloscope into XY mode, and in this case it plots one of the coils against the other. So one coil feeds the horizontal axis, one feeds the vertical axis on the oscilloscope, and we now get a straight line, because they're always in phase, but the relative amplitude changes. So you end up essentially with a system which can determine the position of the coil or the angular position of the coil in the deflection coils. Now if we go back to this again, and we turn the other channel on, so both signals are now, both deflection coils are now being energized. If I put the probe coils in now, you'll see that okay, the amplitude isn't constant, but there's now a phase difference, and as I rotate both the coils, the phase changes. It shifts with the rotation. Now, that's not very interesting, but if we turn back to the XY mode of display, we get quite a nice illustration of what's really going on, and this is showing that we really do have a rotating magnetic field in these coils when we feed the inputs, and the inputs are fed from sources which are 90 degrees out of phase. So the result is that we have a rotating magnetic field inside the coils, and this is what this probe is demonstrating. Now another way of showing that is to put in a simple single turn coil. Okay, this is just a loop of wire, quite light, and if I put it into the coils, what should happen is it should begin to start behaving like a motor, and it does. So it rotates quite readily. We've seen that the single turn rotor like this, while it demonstrates the principle of a rotating magnetic field, we'll detect it, it's of no practical use as a source of mechanical output power. So instead we'll use this, which is the rotor from a washing machine pump motor. It consists of a series of copper conductors embedded in laminated iron sheets, and the ends of the conductors are short-circuited. This is the standard form of the rotor for any kind of induction motor. We've now assembled the motor into a convenient frame, and I've put the original pump impeller onto it so one can see the rotation. And it rotates quite freely, so it's got reasonably good bearings. Here's the complete motor with the two drive waveforms, both at 50 Hz and 90 degree phase shift. If I turn the power on, the motor will run, and it will go at about the synchronous speed for a rotor like that and at that drive frequency. Now what's interesting is to change the frequency of one of the sources by a small amount, and I'll take the top one to 50.05 Hz. And what that does is to cause the phase to change continuously between the top and the bottom waveform on there, and you'll see that the motor only runs when the phase difference is plus or minus 90 degrees. When it's 0 or 180 degrees, the motor doesn't run at all. And this is a useful illustration of how you can change the direction of a two-phase motor in this case. If it's a three-phase motors, all you need to do is invert one of the phases.